Okay, ladies and gentlemen, Alexis Ouellet-Patenaude.
That's the best pronunciation of my name I've seen so far. Well, let's start that. Glad to be here today. My voice is a bit raspy, so at some point I might just go to lunch and forget about you. Okay, I'm not leaving you behind. All right, let's get this show on the road. All right, so you know my name, you know what we're going to do. We're going to talk about our exposure at anchors and ways to simulate it, and use the method of moments to do those assessments and get some insights on what's happening at those particular places. So to start, we'll briefly go over some topics about safety code 6 and why current, contact current and RF fields matter. Why we do this endeavor of being simulating the effects that we see at guy anchors. We'll go over some of the principles, the models, and the methods that we used to develop our methodology. We'll go over some preliminary results, because these things are fresh off the oven, so it's still in the preliminary steps, and you can hear my colleagues wishing me good luck on my job. And then we'll go to like conclusion and next steps, like the things that are ahead for us on the road. So, Safety Code 6 is the guideline by Health Canada that ensures that the public is not overexposed by near non-ionizing radiation in the band of 3 kilohertz to 3 gigahertz, as you all know for sure. It is mandatory for all operators of our systems to comply with Safety Code 6. And what else I put there? Yeah, so you either can demonstrate the compliance to Safety Code 6 by simulations, you can do field measurements, and if you don't comply with those measurements, you have to provide a plan to be compliant. So either install fences, reduce power, all these things that make the levels safe for the public in publicly accessible spaces. So these are typical installations for our broadcast installations that we have throughout Canada. We have broadcasting towers hosting our antennas, and then those towers need to hold something, so they need to be attached to earth or grounded, as I heard before. So in situations where the antenna emits radiations near our guys, the guy wires will pick up that energy and transfer it down to the anchors, and we'll have some re-radiation occurring around the anchors. So that's a phenomenon that we've been noticing for quite a few years, and we know about it. In the last few years, we've developed a bazooka balun method that we can attach to the guy, and this creates a high impedance on the guy wires. It stops the current above the ground, and then at the ground level, you don't have any, well, you have much less radiation going, and makes your site compliant. So that's really nice. However, you have to find out that there's a problem in the first place by measuring that you're overexposed, and you have to get to the site, and you have to do some expenses to get there. So you don't know for sure that a site will be overexposed. You just have to measure, well, that until now. Well, maybe not now, but in the near future. All right, yeah, so the contact currents, it's a thing that when you touch it, you don't have to be overexposed by the current that flows from the metallic energized structure to your finger in your body. That said, there are certain levels of current that are allowable for humans to touch and not be overexposed by the shock of the contact. And these levels are typically enforced for anything that emits frequencies below 110 megahertz or below, which is quite a concern for broadcasting, because in FM everything's happened between 88 and 108. So like there's no way to escape it. So I don't remember if it's it's the GL one that says that neither numerical analysis methods nor current computation modeling simulations are able to accurately assess the levels of present at these locations. There's some quotes involved that I'm not sure, I'm maybe paraphrasing, but it's still there, meaning that the GLY says we cannot measure those things, we cannot simulate those things in advance, but yeah, whoops, there was a challenge accepted. So we have a lot of sites in Canada to measure and to assess. Going to each of those sites is quite a challenge sometimes because there's a very short window where you can actually go to the sites because other times there are polar bears and things preventing you from going to the sites. So there's like a lot of sites to do, not a lot of time to do them. We only have like a few equipments that can measure that thing, so there's like a big logistical issues in doing that process. So if there was a way to simulate those sites without having to go there, that would be a big plus. Okay, so what motivates us? Like I said, traveling time, getting there, lowering our greenhouse carbon footprint by not having to travel to these sites would be great for the future generations. Like if we can know in advance if we have an antenna project coming and we're going to design a new antenna to assess the effect of the placement of the antenna, the aperture we choose, the distance from the guy, if we can know in advance what will be the effect on the ground, and if we have to budget a fence or installation of bazooka balloon, that would be great. So if we know at the design phase that we're going to have an issue, that would be great to know it. And that's pretty much it for the slide. So that's like one of the things, like I said, was going to sites, but once you're in site, there's still a lot of dangers that wait for you. There's mosquitoes, there's wasps, there's the scorching heat that we had like 3 weeks ago. Yeah, I was doing measurements that week, so yeah, it was brutal. Thank you, Veronique, for assisting me. It was great, yes. So yeah, the environment, like you see there, everything is like open and wide and easily accessible. It's not like your typical transmission site. Sometimes you have like snakes, bears, you have to go there on helicopters. You might have fire hazards that prevent you from going to the sites. Moreover, the equipment you have to get to the site weighs like, it's super heavy, it's super cumbersome. Like, I have fallen a few times with it in my hand, and I'm not ashamed to admit it. So yeah, it's pretty heavy, and it's really uncomfortable to have that equipment on you like 8 hours a day doing some measurements, and I've peeled some part of my skin on my finger touching so many metal for 1 week straight. That there's hazards to doing this job. So why we do it? Well, we do it because we can, and how we do it, we choose the method of moment to come to the task. There's a lot of simulations method that we could have used, but they come at the expense of high computational space that you have to model and to simulate. The advantage of the method of moment it is that it's limited to the boundaries of your system. So if you have like a tower structure tube, let's say, you don't have to model the whole tube, you just have to model the exterior. So you save a lot of variables to simulate with that method. Sorry. And since we operate only on a few frequencies in the band, we don't have to simulate the whole band at the whole time. So other methods would not have been suited for this purpose. Also, if you have any questions, I can take them at any time. This way, if I go over the time, I can blame it on you. So, everything good so far? Yeah, great. Yeah, I know, I want to put the onus on. Alright, so first and foremost, why not use NEC? NEC2 is available, you can use it on your computer, it's semi-user friendly. Well, it does not evaluate well E fields and H fields in the near proximity of the fields because there's some discontinuity in charges that appear at the end of the wire. So like a rule is that the wires should not have current at the end because then they would be arcing. So that's one thing that you have to take care of. And then the way that NEC evaluates the field, it's focused at near distance, and that's where we need to assess the fields. So it's no good. Once you have the simulation done, you do not have access to the inner interaction matrix that you need in order to adjust the lumping of the loads. I'll get on to that later. Also, the wires have to be discontinued where they cross. So meaning that they can only touch at the ends of the wire. So if you define a space that, like a tower, it has members, legs, diagonals, guy wires, and everything, and everything has to connect properly in order for NEC to work. That was really bugging because I'm typically going fast in things I do, and sometimes things overlap, and I'm not good for NEC. So we developed our own factoring wire algorithm to solve this. Also, why we implement our own is because we want to bring all technologies into the future. We're broadcast people who want to go to the future, so we'll bring the technologies that were developed in the 70s and bring them to the 21st century. Meaning that most of the tools that would have been candidates for the job have been developed in Fortran or in language that maybe one or two of you knows. But I look at the code and I was not up to the task. So I just rewrote it. Yeah, so while we rewrite the code, we can design the code to fit our need, knowing what we're going to use it in the end. So we, instead of using excitation as peak voltage, we can use power because we use power in the broadcast world. We don't apply voltage to our antenna and expect ERP volts. You have ERP watts. Anyway, and also we have like half the tools already developed to do the task. So this shot here is from the near spot software that we talked in the intro. You already have like an outline of the tower with the tower members and the guys and the antenna and the radiation. So we already have much of what we need, except that the antenna there does not interact with the tower in the previous version of NearSpot that we had. So we needed to have this interaction between the RF field generated by the antenna and the anchors that are below the image, unless it's a really short tower. So back to the high school mathematics. We have the governing equation for the method of moment. Basically, it's a integral over a wire where you evaluate the field strength produced by another source. Yeah, that's really simple, right? Let's get to the example. So on the left of the screen, we have two discrete, let's say, antenna structures that are, let's say, dipoles that are in free space, and there is one of them that is excited at its middle, and the other one is just passively there, waiting to be excited. So you have 8 segments, but you have 6 V dipoles that are overlapping. And so you have your interaction matrix there that you have to fill with the governing equations as we saw previously. So you see the first V dipole, if we cursor, yes, I have a cursor. Yeah. So the V dipole here is imposed a current here of 1 amp, and then you have to measure the potential that 1 amp creates on that segment. So it just integrates the field strength that 1 amp creates. So if you integrate field strength, volts per meter, over a distance, meters, you get volts. And then you divide your volts by the input, which was 1 amp. So if you divide volts by amps, you get resistance or impedance, because we're in RF. And you repeat the process all over again 400 times, and you fill the matrix. Like that. Ooh, yeah, nice image. So these are the governing equations broken down into the basic components of the field. So we have the radial field, the Z field, and the curly H field around the thing. So we have a nice animation of the V dipole exposed by a constant current, which we just make it flip like a reverse torque. And you see the field strength it creates. So the brighter it is, the more power gets there. So you see that the impedance varies because we're just having a constant current. Yeah, at the bottom it's just the 2 parts of the equation. The top part, you see that you have like a blob at the center, which is the discontinuity that I was talking with NEC. So you have like a radiating field from a single source point, and you add it with the bottom part of the V dipole, and then those 2 parts cancel out, and you get the image on the right, which is like the one you see on the left turning, but static. Everything okay so far? Yeah, good. More graphics here. Basically, it's the interactions that I was talking about between the between any 2 V dipoles in your system. So basically, you just take your whole antenna tower structure and you create sections of 2 segments, and those are your V dipoles, and that's how you just factor your whole environment. All right, so once you've done the whole process, it's really like one simple step repeated like n to the square times, and that fills your impedance matrix. So that stays there. And then if you have external sources, you can measure you can measure the potential that excitation creates on each section to create the excitation matrix, which is a linear matrix that's just in 1n space, compared to the impedance matrix, which is a n square space. So,
just question.
Yes.
This impedance is near field or far field or what?
It depends. You could have it near field, but most of the environment in which the tower will operate is in far field of each element. So at this point, we're only using the far field of.
I think it's near, which is very we're measuring like after it's not only almost hour.
Yeah, it's near for like the few guys that are close to the antenna. The rest is far field.
Well, what was it where you was burning your finger to that?
It was at the anchor.
So was that considered near field or far field?
It would be near field, because I'll come back to that. Yeah, it's near field. So, any questions on that? No? Okay. So, once you have your impedance matrix and your current matrix, you just need to solve your system to know what current would create the excitation matrix, excitation vector based on the impedance matrix that you have. So it's just, it's not high school, it's college grade matrix resolution. You can choose whatever solver you want, like a Gauss-Jourdain or LU pivoting table thing. So yeah, once you solve the current, just by inverting the matrix, you get the solution. For example, if we had excited the V2 dipole, we would get that kind of response. So we get the stronger symmetric current on the first antenna and a smaller symmetrical current on the other. So that's an example of solution. It's not really, the math does not work, it's just for example. Other thing that the implementation that we chose is better over AEC is the stability of the solution. Since the V dipoles overlap one another, there's more coupling between them and there's less risk of having a solution diverge. So if you increase the number of segments per wavelength, let's say, you won't gain much of resolution, whereas in NEC that would diverge the more you increase the resolution at some point. All right, so once we developed that new method of moment, we had some testing to do to make sure that it's compliant with like science. The author of that method was kind enough to supply validation tables that you can create your geometry of dipoles and verify the impedance that it has, and then it's good to the resolution that this table has. So there's not a lot of numbers after the dot, so we have the rounding error precision. So we cannot increase the resolution of our model without, like, we're good. Because that was done in the 70s and they only had like 16 bits of resolution, and that took like days to calculate, and it took us like 0.1 second, and we all got the result in 64-bit resolution. So anyway, I'm digressing on purpose. So yeah, the method. Yeah, so once you have your antenna system, you devise your antenna into a matrix of V dipoles. Is there animation? Okay. Then you have to take kind of ground effects, or grounding effects? No, ground effects. So the reflection of one dipole to the other, there's the direct way and there's also the reflected way you have to take into account. You have to take into account the type of soil, the frequency, conductivity, permittivity, those things that will impact the reflection. And if you're connecting your structure to the ground, then you have like to take special care for the segments that touch the ground, which I did not do yet, so that's why the result. Yeah, so once you have your structure, you have to, like I said, I'm doing fast sometimes and I overlap wires, so the software will sort out the overlapping wires, keep only the non-overlapping ones, split the ones where there's intersections, and then it will simplify the solution. So if you have like a long string of wires that are the same radius, it will just recognize that they're all part of the same wire, remove the separation, and then you're gonna have like a long guide wire. And after that, it will split the domain again to fit the frequency that you're trying to simulate. So usually we're going to try to simulate one quarter of the wavelength will be the maximum size of the features that we'll simulate. So depending on the frequency, you might have more or less, depending. So higher frequencies will generate smaller segments and more compute. Once you have that, you pass those dipoles to the impedance matrix calculator, which will define the interactions between all the parts of your system. Let's say that there's no excitation and that it's just the tower, the guy, no antenna is involved yet. And then we calculate the excitation with the antenna that it has on every piece of the environment. And then we get the excitation vector. Once we have the excitation vector in the matrix, we solve it, we get the current, and then with the current we can evaluate the fields, and then we can try to assess the contact currents that are on the field. Okay, so our methodology for the, I'm going to accelerate now. The methodology we used is to make some actual field and contact currents. So we, at the end of July, early August, we went to like 7 sites in Eastern Ontario and did around, I don't know, 1,000 measurement points over the course of the week in gruesome weather. It was horrible. People died. They were not with us, but they like it. Once you have the data, you have to model the, yeah, that's a typical anchor. So you have to touch everything all the time, take measurements. Like I said, the probe weighs 4 pounds, and you have to wear it on your wrist. Like, not on your shoulder where it's easiest, but on the place where it creates the most torque. Yeah, so that's pretty much what you have to do. So you...
Take it off and you go between guys' legs.
That's a good idea. Yeah, take it off in the shower, yeah. Yeah. Dad jokes, right? Yeah.
I got to use it this summer as well.
All right.
Yeah.
Yeah, one of the lucky few. All right, so once you have the measurements, we created the models out of the measurements that we've done, because we have to like measure all the things that we have to measure: the length of the double channel anchor, the width, what's the length of the bolts in the turnbuckle, what diameter is everything. So after all we have the data, we have to put that information in the model and get a you have to take your tower and rewrite it in software using the information you have, which is most often quite well documented in the tower elevation plans, where you have the I call them tower codes, because there's like numbers and they mean things, and we convert those things into actual wire radius and length. And that's what we put in our model. And that's how we convert them to actual radius, because nothing is round and straight in a tower. Everything is like L-shaped and V-shaped, and it's cumbersome. Once we have that, we have to play the game of increasing the resolution of our model. So first we start with a gross model, and we simulate, and then we increase the resolution. Like we increase the level of detail. So we start with an anchor that's only a rod, and we put the shape of an actual double channel anchor, and then we can input the size of the turnbuckle, the bolts, and the things. But it takes time, so we have to find the right balance between the two. Then we compare the measurement and observe the trends in the spread, because we need that in the future for determining the uncertainty. And then we have to do a sensitivity analysis to see how good is our simulation of the tower and the anchors compared to reality, because we used design blueprints of towers. We don't actually go and measure the real height of the things. People do that for us, but sometimes they make mistakes. So just to be sure that we're assessing the best version of the tower that can be, we have to wiggle with the parameters, see the impact, and see if it has a sensibility on the results. And then we determine the overall uncertainty of the process. And for the measurement that we made, the simulation, I would say, we apply that uncertainty and make sure that it complies with the adequate reference levels that are in the safety context. So that's a nice graph of the more complex you get, the higher it costs to simulate and so on. No questions so far? Good. As you can see, it's the first time I'm doing this presentation. I did not practice. So straight to the results. This is one of the sites we measured. It's Bancroft operating at 99.3 megahertz. It's a 300 watt transmitter. The ERP is 269 watts circular, and the antenna is 15 meters above height, above ground, above earth. I don't know. So it has 3 guy wires that join the tower just below the base of the vertical pole of the antenna. Also, the tower is wood, so it's not conductive, so it's like the best bench work for doing tests, because there's only 3 wires involved. So, another simulation result will be for Cornwall. We have a complete tower with guy anchors and tower bracing simulated, and you see that the color scale represents the intensity of the current you would expect on the tower and on the guys. Back to Bancroft, because I'm like that. That's the overall view of the plans and the level of information that we have to work with to create the model, so we get accurate results. So we get like the placement of the antennas, the height, the distance of the guy wires, the size, and the estimates of the guy wires. That's really important, because sometimes you assume that the estimate of a three-phase tower are all 120 degrees, but not all the time. So for the Bancroft case, you have the wire intensity that you would get on the metallic pieces, and also I said there was two wires I highlighted because there's the feed that goes to the antenna that is metallic that you have to consider, and there's the messenger cable that is strung to the building. Words. I'm not good with words. So an overview of the results. On the left column, we have the measurements that we did, the spatial average with the 6-pound beast yellow thing that we saw in the first. And on the right side, we have the simulation results that we got from the simulation results.
So you did upload and simulation.
Sorry?
You did upload. You did the measurement.
Yeah, I did, or Veronique did. I'm not sure who did it. Well, I can know, but I don't know from that picture. But you all see on the right, it's the locations where those measurements were done. Like they have like the vertical path of the probe that we did, and we also have the results of the simulation of the fields produced by those currents at those locations as well, and we're comparing the two. So in the middle, we have the results for that site. So we have an average of 6 dB less simulation than what we actually measured. So that's kind of bad, because we're underestimating the actual field. The minimum is 15 dB, which is bad as well, because we're all underestimating the actual field by 15 dB. Unless that field is quite low, if it produces a field that would exceed the, well, as you can see, none of those fields exceed the limit.
What frequency are you measuring?
It's 99.3 megahertz.
Frequency of that transmission.
Yes. We were using a non-selective probe, so we might have picked up things that were like a kilometer away, but we're most certain that it was produced by the thing that was 5 meters away. Oh, it's just a field measurement at 20 centimeters of the guy along the guide axis.
If you are using a bottom-up FI meter, then you will be measuring the transmission. You're measuring the guide, because it is non-contact. If it is contact, then it's different.
Well, there is no contact at this point. We're going to go to the contact page now. So this is the view from the ground or the earth. I'm going to stick with that joke till the end. So you can see the main radiation of the antenna up there. We can see it's in red, so it's a no-go zone. But you can also see the 3 guide anchors going up and down the tower. And there's one that produces sensible radiation there. But it's not the one that we expected, and it's not the one that we measured was the highest, so that's intriguing. But on the left side, you see the yellow dots are the result of the matrix inversion that gives us the current of the V dipoles. But as you can see, the current goes higher than the current that we measured in the matrix. It's because of the basic function that we use that combines the previous current of the segment and the end current, and they can join force and make stronger current in the middle. So that's how we can reconstruct the waveform with very low information. Yeah, you get the current on the wire, which is maximum 15 milliamps per milliamps. and then the other guys are just like way below. And this is the contact current model that we've developed like 3 days ago, and it's to assess the contact current, because the thing is that all those simulations are great in, like, there's no human involved in the simulation, but with contact current you have to be part of what you're measuring, so you have to touch it. And then one way to do that would be to change your model, add some like wire segments with impedance, lumped impedance that would stimulate the body. Yes.
So in this picture, are you suggesting that if you touch where it's red, you're exceeding safety code 6?
No, the red color is just a scale of the contact current. But yeah, it would exceed. No, I don't remember. Yes, Eddie.
The temperature can be change the impedance, like if it's cold, like it's.
Good question. Yes, in the sense that change in temperature will sag the guys and change the environment and change the impedance. So yeah, temperature does have an effect. We're not at the point in the model where we can simulate the actual sagging with the tension and the temperature, but we'll get there for sure.
What is the theoretical temperature that you take measure to make simulation?
I have no comments. I should go in politics. So, like I said, we made a human matchstick model of where you would contact the place that we measured it was, and then we assessed the electrical fields that are radial and axial on where you touch it. And we divided that matchstick into pieces that we applied a conductivity to it, and then we passed that to a gradient descent algorithm to minimize the error of having the sum of those conductivity with the electrical field give us the contact current. Not even sure what I said. Basically, it's like a minimizing algorithm of optimization, and then what you see is like the locations where we assess the field to minimize. And this is the result. As you see, it does a fairly good job at minimizing the error because the average error is only 0.6 dB. But again, we're underestimating the contact current by, the worst case would be 13.8 dB. So that's like a lot of dBs. So for contact current not to be exceeding the limit, it would need to be extremely low based on our assessment. So yeah, we still have work to do, and that's why it's a work in progress. Other interesting things that we found out during our measurements is that for a single guy that we measured, namely the one on the bottom right here, the contact current that you would be measuring with a clamp would be varying a lot depending on where you are when you touch the same place. So if you touch the contact here or here, you would get widely different results, but you're touching at the same place. So like that's what triggered us into thinking that the place where you are actually influences the contact current that you're measuring. So that's why the matchstick model depends on the position where you are when you do the contact current.
Are you using a probe to do the high measurement?
Yeah, I think it was slide number 4. We can go back. I have like 1 minute. I just want to be on time. And so, as you can see, the orange and the green one are from 2 different persons on the same side, and they're quite similar. Interesting. And the blue one is from another person on the other side, and they're widely different, but they're the same locations. So that's really interesting. Next step. We need to do a sensibility analysis on our parameters to see where to put our focus next on what elements of the model we need to improve. We need to harmonize the propagation model because the excitation, the interaction, and the field of the reaction methods do not all use the same ground properties. They're like one that is in free space, the other one is with ground, but it's perfectly conducted ground, and the other is like using actual ground conductivities and parameters. So yeah, I'm into the negatives of them. Next step would be to implement surface scattering. So instead of using wires to represent things that are not wires, use actual 3D volumes and facets that would scatter the electromagnetics better than wire do. Also the underground interactions. So most of the anchors are below ground, and there's potentially things that happen there that we need to capture in order to be able to actually predict the contact rates better than our 13 dB difference that we have in the previous slides. More measurements, because like we said, we did assess the sites in scorching 30-degree plus weather, but we don't know what happened below 30 degrees. Is it better? Is it worse? So we had to do measurements at reasonable temperature next time. Like autumn is good to do that. And then we have to present to our friends in ICED our model to make sure that it's compliant and it's rigorous and it's something that can be used throughout our whole range of sites that we have in Canada. And yeah, question, comment? Yes?
Will you be able to use this to predict which of the guy wires arrive with the anchor you need to put the bazooka on?
Yes. And we will probably be able to predict the effect and the isolation. Yes. Next, yes.
Yeah, in my understanding, since you are measuring some current on the guy wires are acting as a radiating element. Extra radiating element.
Yeah, sure. Yeah,
It becomes part of the antenna system.
yeah, the thing I said I would come back to is that slide here where you have the current on the guy wire.
Yes.
So each lump goes in one direction and the next lump goes into the other.
Yeah, so that's why it's a radiating element now.
Yeah.
However, other engineers, I find that they put something on the guy wire for snow prevention.
Yeah, the Crosby
So
clips.
So they clamp the guy wires on the ground on another side, so that it is for snow, but not for your safety code 6 and purpose.
Well,
And in that case, the guy wire becomes grounded. In your case, is your guy wire grounded there or no?
there's a ground, but it's parallel to the guy wire.
It's not grounded actually, it's only on the cement, right?
No, it's a rod that goes to the ground.
Is it direct to the ground? Or
I have pictures to prove it.
I
I was there. I've seen it. I've touched it. Yeah, the thing is that it's a near field environment because you don't sit on this graph, but each lump goes into the opposite direction than the next. So that's the typical thing that we see in a standing wave form. So we get like the current going down, being reflected at the ground and going back up. So we're going to have some standing wave there. And the fact that it's near field is because the effect of one lobe is cancelled out by the other. So as you move the weight, you get less and less radiation. So that's why it does not radiate as well as an antenna, and it fades really quickly because of that.
Another portion of the CBC is that they put something on the ground, guy wire, so that it prevents those things, right?
Yes.
Yeah, you call it the bazooka.
Bazooka Belden.
Bazooka.
Where were you 5 years ago when I was here? Next.
Any speculation on why the location of the person, even though they're touching the guy wire in the same place, the location had such an impact?
In that case, there was a messenger guy going above one side of the guy wire. There's a building also to the back, so that might have, I did not capture the building in my simulations, but it might have increased the field on one side and less to the other. There might be some buried ground. Yeah, there was buried grounds, we know that for sure, but we did not capture it in our simulation. And the models that we use for the antenna excitation In this case, it's not a actual antenna. It's not like a ring antenna that we measure the phase difference in the azimuth and all. It's just a point in space that we just assess the actual phase of those points.
You just have to be, you and I can put the bracelet on, we can stand in the same place and touch. Based on my experience in the spring, we will not get the same number. It may even be a magnitude difference.
Yeah, exactly. Anthony,
You
yes.
said measurement. Are you doing any peripheral measurements like ground soil humidity or air humidity or temperature? Do you do daytime measurements?
We have temperature because we have to take into account for acidity of our equipment.
Okay.
We have, yeah, that's it. No, we have like a ground resistivity probes that will tell us the resistivity, but it only tells us in DC, so I don't know if it's good at 100 meg.
Like, do you?
Maybe it is, but
Do you have any other electrical measurements that are referencing the transmitter or the earthing point of the actual transmitter itself? Like you say, do you have special shoes that are copper clad, is there anything like you say, like you're seeing these minute differences based on even who and what, and maybe what they're wearing in impacting these current measurements? What are you doing to better understand these variables?
yes.
I'll take it.
On that note,